got the line y equals 2x. One thing I'd really love us to understand is that every point on this line, like let's say the point 3, 6, has this relationship that the y coordinate is exactly twice as big as the x coordinate. The y is twice as big as this x. If you go over to where x is 8 and you go up to this point right here that's on the line, when x is 8, y is 16. Of course it is, because y has to be exactly twice as big as x. Any point that has that relationship between the two coordinates is on this line. That is why the line graphs all the solutions, all the ordered pairs that make that true. Any point on this line has the basic relationship that when x is x, y is double that amount. Keeping that in mind, when we do a problem like this, when we want to find all the values, all the ordered pairs for which y is greater than 2x, we're going to start with this line, which is the line y equals 2x. The points on this line are, again, the points like 3, 6 and 7, 14, where y is exactly twice what the x value is. But if we're going to find these ordered pairs for which y is more than twice x, then all we have to do is say, oh, okay, well, let's go down here. When x is 3, we can't have y be 6. We need y to be more than twice x. So we could pick when x is 3, y would be 8, or when x is 3, y would be 11, or y would be 18. Because we got to pick any ordered pair for which the y, in this case 18, is more than twice what the x is. Likewise, when x is 7 and y is 14, that's a point that's on this line. But any point that has this relationship, when you put 7 in for x, you need to get back more than 14 for y, because the y needs to be more than double whatever the x is. So those are points up there. Well, pretty soon what you realize is any ordered pair that is above this line will have this relationship, like right here, when x is 1, y is 14. Y is more than twice what x is. So, pretty soon you realize, oh, these points out here, there's infinitely many of them. I'm tired, I'm just going to shade it in. All those points eventually would fill in that whole side. There's the solutions to that inequality. All the points have that relationship between y and x. Okay, what about if y is less than 2x? Well, same thing, only on the other side. We have a point right here that's 4 and 8 that's on the line. Pick any point that's down below the line, and that would have the relationship, like this point here, of x being 4 and y being 3. Y is less than twice what x is. So just like on the problem before, any point that's on this side of the line, like this point right here, where y is 9, or x is 9 and y is 15, that y value is less than twice what that x value is. So we realize that the infinitely many ordered pairs that are on this side of the line are the solutions to that inequality. Go back to this inequality with just one variable. We took away 7 from both sides. We got that 2x is greater than 8, divide by 2. We get the solution set being any x that's greater than 4. It's only one variable, so it's one-dimensional, so it's just the number line, the x-axis, if you will. And we said, okay, 4 is the boundary. 4 separates the solutions, the x values that are greater than 4, all these points up here. Any point up here on the line gives you a solution to this inequality because it's where all the x's are greater than 4. Now the boundary is at 4 and x is only greater than 4, it can't equal 4. So remember, we put an open circle at 4 stipulating that x can't equal 4, but it can be any number just above. And in the end, all those infinitely many dots just filled in to be a shaded line. That's a beautiful shaded line right there. But what did we do? We found a boundary on the x-axis that separated the solutions from the non-solutions. And that's what we're doing here. Our boundary now is a line. When it comes to inequalities involving two variables, linear inequalities, the boundary is a line. On one side are all the points that are solutions. On the other side, none of the solutions. So, boundary, solutions, not solutions. Boundary is a line, solutions, not solutions. So if we start to put all this together, we get an approach for graphing solutions of linear inequalities. I would say graph the boundary line first that separates the solutions from the non-solutions. That involves treating this like it was an equation. So for a moment, ignore that it's greater than or equal to this, and graph this inequality with a y-intercept at 5, and a slope of -2, so down 2 over 1, down 2 over 1. So we get a line that looks about like, okay, we're going to do the best we can here. A line that looks about like so. That's just beautiful. Now, any ordered pair that's on this line would have the characteristic that y would equal exactly -2 times the x-coordinate plus 5. But we also need to add all the ordered pairs for which the y-coordinate exceeds or is greater than -2 times the x plus 5. Well, my hunch is it would be points that are above this line. So let's try like this point right here. This is the point 0, 12. So here's what we're doing next. See, we're going to graph the boundary line. If it's less than or greater than or not equal to, it's dotted. But this one is a greater than or equal to, so we leave this line as solid. All the points in this line are also solutions to that inequality. Now we're going to shade the side of the line with the solutions. We pick a point that's not on the line. Here's an easy point to pick. If x is 0, y is 12. Put a 12 in for y and a 0 in for x. Is 12 greater than or equal to -2 times 0 plus 5? Well, this is 0. 0 plus 5 is 5. We're left with the statement that 12 is greater than or equal to 5. That's a true statement, meaning that this ordered pair is a solution to this inequality. So it must be this side of the line that has all the solutions. So in the end, we're going to shade that side of the line. Any point on that side is going to have ordered pairs with this characteristic. The y-coordinate is more than -2 times the x-coordinate plus 5. One of the easiest points to pick to work with that's not on a line to be able to decipher this is really the point 0, 0, the origin. If you put a 0 in for y and a 0 in for x, you would end up with 0 being greater than or equal to 0 plus 5. It is not true that 0 is greater than or equal to 5, so that substantiates the fact that on this side of the line are no solutions. Boundary, solutions, no solutions. Boundary, solutions, no solutions. Boundary, solutions, no solutions. So we got the same thing going on here. If we did this now, if this is an equation, remember the two easiest points to find to make this equation true are put a 0 in for x and see what y is. 2 times 0 is 0, so y would have to be -4 in order to make this true. So when x is 0, y is -4. And when y is 0, that would be -3 times 0 is 0. 2x is 12, so x would have to be 6. So this is an ordered pair combination. When you have 6 for x and 0 for y, and when you have 0 for x and -4 for y, then this line contains all the points on it, all the ordered pairs for which this 2x minus 3y is equal to 12. Now, if we're going to do this inequality, we start by graphing that line. But I'm going to graph this line as a dotted line. So we're going to go through this point right here. So we're going to go and go right through here. So that would be the dotted line close enough that represents this equation. Now when we're solving this inequality, we start again by graphing the boundary to where the solutions would be. It's dotted because this is less than. We can't have any points that are exactly on the line like these two ordered pairs. They wouldn't be solutions for this. 0 minus 0 is not less than 12, or I'm sorry, 0 minus -12 is not less than 12 anyways. Those points on the line would be no good. Now we've got the boundary line. It's dotted because we have a less than sign. On one side are all the solutions, on the other side are no solutions. So what we're going to do is we're going to find the point 0, 0 and put it in here. 0 minus 0 is less than 12. That's a true statement, and so all the points that are above this line will make this inequality true. So that's where we shade. That's where we find the solutions. The points on this side of the line would not be solutions to the problem. So there you go. That's graphing inequalities.